don't know why that's up. Okay, weird. Anyway, so the first three problems wanted you to sketch some graphs and then find the area bound by those two graphs. So problem number one gave us two functions and bounds, or you can even actually think of those not as functions, but as lines that you can graph. X equals -2 is just a vertical line. X equals 1 is just a vertical line. So all of these are things that you should have kind of an idea of what they look like in your head. X squared plus 2 is a parabola that opens up and has a y-intercept of 2. And negative x is a diagonal line, perfectly diagonal line, that goes through the origin and has a negative slope. I guess by perfectly diagonal, I mean it just goes, it goes right through each of the grid line squares, I should say. So those two things do not intersect. If you set them equal to each other, you'd get a quadratic that when you did it, you'd have to go quadratic formula and you would get a negative under the square root bar. So that's kind of the, when that happens, it's because your two lines don't intersect, which is why they gave us x equals -2 and x equals 1, which are vertical lines, which do intersect both those curves. So they wanted us to find basically this area here. I got a little pen on my button that changes it to erase that I never actually remember about when I want to erase. Okay. So this is probably the simplest problem we could have. They gave us the bounds, so we're going to integrate from -2 to 1. We know that the parabola is on top, so we're going to integrate x squared plus 2. And then it's going to be f of x. The formula is f of x minus g of x. So I'm going to put minus -x. Correct. So there we go. Could you have plus x there? Absolutely. I put the minus -x there just to emphasize the formula. Yes. True. Yeah, no, I mean, if it does say write but not evaluate on an FRQ, you are allowed to do that. So yeah, yep. Yeah, nothing wrong with that. So our next one, yeah, you won't be able to do that for number 3, but for our next one, we have a downward facing parabola with, for some reason, a y-intercept of 6, which meant it was off. There are only 5 lines there, right? Yeah. Okay. But it is downward facing, so it goes kind of like this. We have the line g of x equals x, so we do have that perfectly diagonal line. We could clean this up once we find those actual intercepts, but we do have to solve 6 minus x squared equals x to figure out those 2 points where the parabola and the line intersect. So suggestion, bring your x squared term over to the right so it's positive, and you end up with x squared plus x minus 6. Just for space, I'm going to write it this way. X squared plus x minus 6 equals 0, which gives us x plus 3, x minus 2, which means that those values are x equals -3 and x equals 2. So actually I didn't do too bad with my drawing, surprisingly. This is 2 comma, I'm going to guess, 2, because the function is g of x equals x. One step ahead of myself in my brain. And this is the point -3 comma -3. You don't need those y values. It just seems like every example I've done so far, those y values have been simple to figure out. I'm impressed at how decently well my parabola turned out. Thank you. If I had wanted it to turn out that well, it would have been a disaster. Okay, so now we have our bounds for integration. So it is the integral from -3 to +2. My upper function is the parabola, so I can do it in the requested way. I'll just write f of x minus g of x dx. All right, cool.
Why can you not do that?
Well, you can if you can. I feel like it's more work to do it that way. Yeah, if you want to define, and that actually is a legit thing you could do on an FRQ, you can define a new function and use it. Franklin just called the first one f of x, the second one g of x, and the third one h of x in possibly a different order. But I'm not going to do that because I don't want to. But you can do that if that's what you want to do. So last one, it's all just lines. We have y equals x, which is the perfect diagonal through the origin. We have 4 minus x, which is another perfect diagonal, but it goes through y equals 4 and goes down. Being that we were provided this x and y axis, we don't even need to solve for that point and the fact that they're perfect diagonals. That intersection is right there. And we've got an intersection there and an intersection there. The upper function changes, right? The line with the positive slope is the upper function for the first half of this, and then the line with the negative slope is the upper function for the second half of this. So we need to do two separate integrals. The first one from -1 to 2, and then the next one from 2 to 5. So these are the things you have to start thinking about in all of these geometry problems. Just kind of what is going on here. Do I have a simple one integral deal, or do I have a multi-integral deal? And if your upper and lower functions happen to change, you need to use more than one integral. So, like I said, we'll integrate from -1 to 2, and then we'll integrate from 2 to 5. And we're adding them because that reflects what we would do if we were just doing this with areas, right? Because in the end, I could just do this problem with areas. I've got two 3x3 triangles. So we should end up with 9 as our answer, right? Because each one of them would be half a 9. But we're not going to actually evaluate, so we won't actually get there. So my upper function is x, and my lower function is always -1. So this is going to be x plus 1 dx. And the other way around, it's going to be 4 minus x, again, plus 1 dx. And that plus 1 just comes from minus -1, right? This time I didn't show that. And that is a minus sign, despite the fact it doesn't look like it. Okay. So I don't think any of this is terribly hard. It's just that you kind of have to adjust to it, right? It felt very different than a lot of the things we did yesterday. But hopefully that explanation of those three, it's like, oh, okay, that's what they gave me. This is what I have to do. Okay. Cool. All right. Let's take a look at 2 more examples, and then you'll have time to work. This is based off they've asked questions like this multiple times in FRQs. So these sections 5 through 8 represent a bunch of questions that can be asked on the same FRQ. So it's really common for one of your FRQs to be some sort of graph, and then they ask questions from all 3 sections, and that becomes an FRQ. And here's one of those questions. We have some sort of region. We have the equations that give us our region, and we want to split this into 2 regions of equal area. I guess this one doesn't say calculator active, so I guess we can probably do this one. But that so I agree. Except it says the line x equals k, so we're looking for a vertical line. So if I took a vertical line and just put it down the middle, I don't think those are going to be equal areas because this is kind of fatter in here and this is kind of skinnier up there. So it's not as simple as just cutting the thing in half. We want to split the area. This should make sense. Like these things that I'm doing, although they are answering specific questions, you really want to understand like the idea behind it. Why am I doing this? Why does this thing work? And if it makes sense to you, that should help you remember to do this. Basically, what we're going to do is we're going to, if we have 2 equal areas, we're going to set 2 integrals equal to each other because each integral represents the area. The first integral is going to start at 0 and go to, I don't really know where. So k, x equals k. The integral on the other side is going to pick back up at k and go to 4. And, those numbers are coming from the fact that that's where our area's x values are. It goes from 0 to 4. we need to be able to figure out which of those functions is which. So we have y equals 2 square root of x and y equals x squared over 4. Which is the upper function? 2 square root of x, yeah. So a square root function is really just a parabola tipped on its side, but then with the lower half cut off. So that was a lot of words there. So yeah, so like y equals just plain old the square root of x is the same thing as square both sides, x equals y squared. So you've just flip-flopped where x and y are in y equals x squared. So this is x equals y squared. It's a sideways parabola. Now, instead of y equals x squared, which would be a horizontal parabola. But then when you do square roots, because our function is y equals square root of x, you're only allowed positive y values. You make it a function by eliminating that part of the parabola. Okay? So that's what a square root function looks like. And then obviously x squared over 4 is also a parabola, but again, it was kind of cut off just because the problem cut it off that way. It didn't show it going over here. It didn't show any of the extensions. So anyway, this is definitely one side of a parabola. So that's, how I've kind of figured out which function is which. All right, so from there, it's just a matter of putting f of x minus g of x on both sides. So we end up with 2 square root of x minus x squared over 4 dx, and then the same thing over here. Dx, thank you. All righty. Okay, so we have to take the same antiderivative twice. I do believe this does work out. I haven't done this one since last year, but I remember this one where something is going to be somewhat nice here. So we need an antiderivative for 2 square root of x.
Yeah. No.
4 square root of, not 3.
X of x.
Yeah, 4 square root of x. So 2 square root of x is 2x to the 1/2 power, which means when we integrate, this is not good notation up at the top. I drew an arrow, so I'm not saying these things are equal. But when we integrate, we have to make that x to the 3/2, and we have to take the 2 and multiply it by the reciprocal of that. So that's where 4/3 x to the 3/2 came from, or 4/3 square root of x cubed. Which again, we are going to take the square root and then cube that. So I say the square root of x cubed, but I'm going to take the square root of x and then cube it. Okay, so we've got that one, 4/3 square root of x cubed. Did I miss anything? No. And then we're going to do minus x squared over 4 becomes, yep. And we've got to evaluate that from 0, that's easy, to k, that's actually also easy. Because evaluating it at k is just putting k's where all the x's were. Yeah. So that side isn't too bad. I think out of the 3 of these, I think there's only one math we're going to have to do here. One math we're going to have to do. I stick by my wording. Leaving a little space just so it doesn't get clogged up with that k that I wrote too big. 4/3 x cubed minus x cubed over 12. And that is also evaluated from k to 4. All right. What's that? Yep. So the only thing we're actually going to have to do here is plug 4 into this. But honestly, we don't have to do too much math. You'll kind of see what happens because you don't need to have just plain number answers on open-ended on FRQs. So anyway, on our left side, we end up with 4/3 the cube root of k, or the square root of k cubed. Sorry, I mixed things up there. Minus k cubed over 12. Yep. Nope. Which is, and then we have a minus 0, but I'm not going to write it. On the right, here we have the math, 4/3 the square root of 4 cubed minus 4 cubed over 12. and then minus the quantity 4/3 square root of k cubed minus k cubed over 12. Okay. All right. That looks like a disaster, but I swear it's not. Right. So don't distribute the minus. This is common to these questions. You have a thing on your left-hand side, which is this. And then you have that same thing with the minus on the other side. So add this thing to both sides, and you end up with 2 times that thing. Maybe this is a calculator active question. Yeah, I'm just realizing that there's one more part to this that 2. So we've got 2 times that thing. Yeah, this definitely is. That's why it's. I was remembering this part about it, but there's one step after this. Boom. Yep. But here's why. Yeah, this absolutely is calculated. There's no way we're doing this thing by hand. This just goes into Desmos. Left-hand side with x on one line, right-hand side with as is on the right line, and we figure out where that k value is. I wouldn't do a slider because you need to make sure you're perfectly accurate, and it might be like 18 decimal places. Yep. Okay. It also might not be, right? But you don't know, so yeah. So here's what I'm going to do. I've got 2, the quantity, 4/3, square root of x, but cubed, minus k cubed over 12. That's going to be over 12 divided by 12. Really do like doing this on the computer better. And then on the right-hand side, basically almost the same thing, but with a 4 placed in for the x and no 2. So 4/3, the square root, I don't even need to do the math here, of 4 cubed minus 4 cubed over 12. Nope. Thought I hit the button. All right. Yeah. And I've got to put a y equals in front of that to get it to graph. Boom. And there'd be our answer. What's the x value? 1.764. Correct. K value. Yeah, the k value. Yep. Wrong computer. 1.764. You don't write Desmos. This isn't what I would write on an FRQ, but yeah. Yeah. Alrighty. All right. Okay, the last problem, the last example problem, which we're going to look at in kind of 2 different lights, whether it is calculator active versus whether it isn't calculator active. And the calculator active part is really going to relate to what we wrote on our card yesterday for this problem. If you have a non-calculator active problem and you have a situation like this where your 2 curves cross multiple times, you're going to have that same situation we had in the third problem we started class with. So the things that you worked on yesterday, where your upper and lower functions are going to change. We have a cubic function and we have a quadratic function. So we have something with an x cubed and something with an x squared. The cubic function is the upper function in the first part of this, but then it switches roles to the lower function. So in one case, we'll have to do f of g minus g, or f minus g, I should say. And then in the other case, we'll have to do g minus f. in both cases, we are just keeping the thing positive. That's why our actual formula allows us to just use absolute value and then don't worry about what order you put them in. Unfortunately, we if we have to do an absolute value integral by hand, we have to worry about what order we put them in, because absolute value isn't just like a function we know what to do with. We have to figure it out. Okay, so anyway, I think this ends up being, again, another one where if you understand why we're doing it, it should make complete sense. I have 2 intersection points there, and I have another 2 there, and f of g is on top for the first half. So I need to integrate from -2 to 0, f minus g, and then add the integral from 0 to 2 of g of x minus f of x. So you guys go ahead and do that. We got Kranek. Hey. That's good. No, you're good. Right. Yep. Yep. Right. That's the idea. Yep. I mean, my thought is, my goal is that we're going to lose the Amy created spreadsheet with all the colors, and you're just going to do the spreadsheet out of Linkit. I think that was in the first set of instructions that I gave you. Yeah. So yeah, so if you follow the Linkit math dashboard instructions, that takes you all the way to making the spreadsheet. Yep. Yeah, that takes you all the way to printing the spreadsheet. And yeah, it's there in Linkit, and anytime you need that, you can download the spreadsheet and save it, and then you have the saved spreadsheet. But if you ever need it again, it literally will take you a second to do all that stuff that we used to always do by hand. Yeah. Yep. I mean, then use it wisely to do things that you actually need to get done instead of doing things that you don't need to get done. Yeah. Mm-hmm. Right. Right. Yeah. No problem. All right. You too. Bye. Yep. Yeah. Sure. Okay. So yeah. So you label them as f of g. Yep. That works. Yeah. Yeah. Because you're just redefining a different function. Yep. Yeah. I like that. Okay. All right. Clean this up and. Aha. Did anybody see this? Good. Yeah. It probably canceled before you did this, actually, didn't it? Yeah. If I did, I just went right to antiderivatives. Gotcha. But yeah, they would cancel. I was thinking there was a lot of little things in this one. So that's from -2 to 0. A lot of repeat calculations in this one. So we end up with, yep. Actually just make this 6x squared too. I'm just going to do it. 12 minus 20 minus 4. Yeah, I don't know why. I feel like I'm getting the... That shouldn't happen. Both areas should be positive. Uh-oh. Yeah, both areas need to be positive. If you get a negative area, you haven't put the correct function on top. And x squared. It's the x squareds that cancel out. They're the only odd ones. Nope, I have the... I mean, yeah. Are these the numbers we're all getting? So the thing, by making sure the upper function is on top, that's why we're not using absolute value. Putting the upper function on top is ensuring that we're working with an absolute value. Those two things are the same, are one and the same. So what are we missing here? 12 minus 20. It's the -2 never really. All right, quick Desmos here. Make sure I didn't mess up the drawing. I can't imagine me not writing myself a note if it was wrong. So f of x equals 3x cubed minus x squared minus 10x but the thirds cancel out, so you shouldn't have any thirds. And then g of x is 2x minus x squared.
Oh, me too.
Okay. So we're, yeah, no, so my graph is correct. Let's see which, all right, so what did you guys get for the first integral? 12? 3x to the fourth, so 3 times 2 to the fourth over 4 is 3 times, oh, is this 3 times 4? 12. Oh, here's right. Is this, I swear, is it this? This is where I'm wrong. Oh, so it's 0 minus 12 minus 20. But then that should be minus the, oh yeah, no, minus the x squared, which is 4, which gives me 0 minus, let's double check. Let's pre-populate our answer so we know what we're trying to get and see if we actually get it. F of x minus g of x dx. It's going to be mad at me because I didn't use parentheses because it's the worst. 12. All right, so we should be getting 12 here. Why am I not getting 12? Oh yeah, I'm 20 minus 24. Oh yeah, this is 12. Yep. Yeah. I kept doing 16 here, but that's not right because it's negative 20 minus 4. Okay. All right. So this we're plugging in. All right, so I should be starting with 4. Yeah. 2 squared. I don't know where I got that first number from. Minus the quantity. And it's going to be 12 minus 20. There we go. Oh, gotcha. Yep. There we go. Yep. Thank you. Boom. Yeah, there we go. That also equals 12. Yep. Just the simple math of it all. Yeah. So there we go. And then 12 plus 12 equals 24. So when you are keeping, and again, why we're doing what we're doing, when you're keeping your f of x over your g of x, you're doing absolute value. Splitting the f of x minus g of x, or changing the direction or the order of f of x minus g of x, you are doing the absolute value. So if I ask Desmos to integrate the absolute value, it will give me the correct answer. So let's take a look at that. It's the wrong Desmos. Did I do Desmos on my computer? Is that what I did? Got multiple Desmoses going on. If I do the integral from -2, Franklin, is that an 8-0 number? If it is, answer it in network. Yeah. It was the same person who called before. Kranek. Hey, what's up? I do. You're borrowing them? I'll get them back all erased and stuff. Yeah. Perfect. Yeah. Yeah. How many do you need about? I have like 2 500 packs and they have to make it through finals. Yeah. Right. Okay. Yeah, we're low. I thought I had more sitting in the closet, and then I realized I didn't. But they came in. They were actually, I ordered them for this year. They just came in a couple days ago. So. I put them in for this year, last year. So yeah. Like, and I didn't realize they didn't come in until Amanda sent me an email the other day. Hey, did your Scantrons come yet? I'm like, what Scantrons? Because I don't think about them until finals time. Yeah. There's also other options too. There's like, it doesn't. Yeah, I mean, there's like ways to do it with like online bubble sheets too that aren't too bad. That you can just kind of like run through the copier if you don't find anything. We can talk about that sometime when I'm not in the middle of a calc lecture. All right, I'll talk to you. But all right, cool. All right. Boom. All right. So yeah. So, if you have a calculator active problem, the absolute value takes care of the legwork of you breaking up the integral into multiple pieces. That's really the key to this. The absolute value kind of saves you on that one. And it doesn't matter what order it's absolute value. So whether I do f of x minus g of x or g of x minus f of x, because you're absolute valuing it, it doesn't care. So, you don't even have if your calculator active, that's what you do. When you see an integral like this that you have to solve, you have to go through the process of finding where one thing is bigger than the other and breaking it up into separate integrals. So that's when you see that absolute value inside an integral, that's what it's telling you to do. If you have a calculator, awesome, just use it. If not, you got to figure out which one's bigger and when, and then break yourself up into separate integrals. All righty. All right, so much for having a pile of